There is one more way of figuring out whether your function has a max or a min other than using the first derivatives test, and that's called the second derivatives test. And I would say that a well-crafted question can get you to use this test, but if you're given the function itself, then you can't fail by just using the first derivatives test. The second derivatives test might be quicker, but it would have to be a really well-intended question to get you to actually be forced to use the second derivatives test. And I'll do an example of that type of question later on. But first, let's just remember that the second derivative tells us about concavity, whereas the first derivative tells us about direction of the curve. So if f prime of c is 0, we know, for instance, we know that, let's say this is c, we know that basically, we know that much about the curve. Let's just say that's the y value. It's doing that. Now if the second derivative at that moment is less than 0, that means the curve is concave down. And a concave down graph must look something like that, at least around c. And so you can see there we have a local max. On the other hand, if the derivative is 0 at c, and the second derivative at c is positive, that means it's concave up. And that means the graph must look like that, at least around c. And that gives us a local min. I should say that it's happening at x equals c. So right off the bat you can see the advantage, right? If you know the first derivative is 0 and you don't want to make an f prime number line and do the first derivatives test, you might just try taking the second derivative and plugging in the c value. And if it's positive, you know that you have a min, which again that seems weird. If it's positive, why is there a min? Because it's concave up. So just think smiles for concave up and frowns for concave down. But in any case, it could get you to that answer more quickly. However, if the second derivative is 0, if the first derivative is 0 and the second derivative is 0, you can't use this test. And this graph will convince you why. Let's take a look at, for instance, f of x equals x to the fourth. That looks like this. It's like a parabola, but flatter at the bottom. So it basically looks like a parabola. We know we have a min there, right? But the first derivative is 4x cubed, and f prime is 0 is 0. However, the second derivative is 12x squared, and the second derivative is 0, and we have a min. But all that would still be true if I put a negative in front of this and graphed negative 4x, or negative x to the fourth. All of what I just said would still be true, at least in terms of the values at 0. You just have negatives in front, and in that case you have a max. So the second derivative being 0 does not help. It doesn't tell us anything. We can't use that test if that happens. So I hope I made that clear. This is the classic counterexample, because in both of these instances the second derivative is equal to 0, but in one case you have a max, in one case you have a min. So that means it can't be a reliable test in that situation. But otherwise it actually is. So you can see the advantage of using the second derivative test in an example like this. So let's do it two ways. Let's first use the first derivatives test, and then we'll see how much easier it would have been maybe to use the second derivatives test. So I've got f of x, f prime is going to be 3x squared minus 3. And if I factor that, it becomes 3 times x squared minus 1, which is 3 times x plus 1, x minus 1. And if we set that equal to 0, we get that x equals negative 1 and x equals 1. So at -1 and 1, this is f prime. I'm doing this quickly because I know I've already covered it. Let's plug in 0. F prime of 0 is, plug it into the top version. It's negative because it's 3 times 0 squared minus 3, which is negative. F prime of 2 is going to be 3 times 2 squared minus 3, which ends up being positive. And the same thing should be true at -2 because -2 squared is the same as 2 squared. So we can see that we have a local max here, and we have a local min here. And so we would say, now I guess they asked for the local extreme value, so the local extreme value, well, let's not do that yet. Let's just determine, let's see if we could do this using the second derivatives test now instead. So there's the first derivatives test. This is the first derivatives test. If we use the second derivatives test, it would look like this. You would say f prime of x equals 3x squared minus 3 and you'd find the critical points. So you'd find that the critical points are x equals 1 and -1. So the first derivative is 0 at those times, and if I find the second derivative, which ends up being 6x, then you can determine whether we have maxes or mins at those instances by plugging those values into the second derivative. So f double prime of 1 gives me 6 times 1, which is 6, and that's greater than 0. So that must mean we have a minimum, right? Because that means concave up. So let's actually write that concave up, which implies we have a min. And if we plug in -1 into the second derivative, we get 6 times -1, which is -6, which is less than 0. And that implies concave down. And that implies a max at x equals 1. And notice all of that is confirmed. All of that is confirmed by our graph up here, right? We definitely have a min at x equals 1, a local min, and we have a max at x equals, I didn't write that in well enough, we have a max at x equals -1. So the second derivative got us to that realization more quickly, so it's an option for sure. However, the first derivative should always work as long as you're given all the information about the function itself. All right. It asks for the local extreme value, so we would just plug in. We'd plug 1 into our function and get 1 cubed minus 3 times 1 plus 2, which gives me 0, and f of -1 would be -1 cubed minus 3 times -1 plus 2, which gives me -1 minus 3 plus 2, which is, sorry, -1 plus 3. So that gives me 4. So it looks like we would say we have a local min value of 0 and a local max value of 4. Alright, so again, the thing to appreciate is the second derivatives test here made it maybe probably a little more made it a quicker problem, I guess I should say. A quicker problem than using the first derivatives test. So it's an option for sure. Make sure the first condition is met, which is that the first derivative equals 0 at those points that you're analyzing. Here we're going to look at a situation in which we have no choice but to use the second derivative test to figure out if there's a max or a min at a certain point. And the reason is, if you look at the way, first of all, we're not even given the function, we're given its derivative, and we're given its derivative in terms of x and y. So that means we can't set that, we could set that equal to 0, but we're not going to get anywhere because we're never going to be able to find actual values where that derivative is equal to 0. We'll have a relationship between x and y, but that's not enough. So I'm just going to note, we can't use the first derivative test. In other words, we can't do an f prime number line. So we must use the second derivative test. So this problem is written in such a way that we're forced to use that test. So, first of all, notice that dy dx evaluated at that point is equal to 5 times 1 minus 5, which is 0. And that needs to happen, right? We need to, if there's a max or min, we need that first derivative to be equal to 0 to use the second derivative test. So now we take a look at the second derivative. Now the second derivative is going to be the derivative of the derivative. So that equals 5 minus 1 times dy dx, because we need to use implicit differentiation. But dy dx is the same as 5x minus y, so this is just 5 minus 5x minus y, which is equal to 5 minus 5x plus y. So now we evaluate the second derivative at the point we're interested in. So that's 5 minus 5 times 1 plus 5, and that equals 5. And 5 is greater than 0, which means our graph is concave up. And so if it's concave up and the first derivative is 0, we know we're looking at something like this. So that must mean we have a local min. So that all means we have a local min at 1, 5 by the second derivatives test. Okay, so there's a situation where you'd be forced to use the second derivatives test.